Let's do a few example problems from page 351 out of section 2.3. I want to go over problems 43, 47, 54, 61, and 74. The first four of those problems have these instructions. Use the leading coefficient test to determine the graph's end behavior. Find the x-intercept. State whether the graph crosses the x-axis or touches the x-axis and turns around at each intercept. That's going to make us know the multiplicity for each zero. Find the y-intercept. Determine whether the graph has y-axis symmetry, origin symmetry, or neither. If necessary, find a few additional points and graph the function. Use the maximum number of turning points to check whether it is drawn correctly. Alright, well let's go on and get started with question number 43. Now you might notice that the page number I just said, page 351, doesn't match what we see here. I'm actually working out an older edition of the textbook, but I verified that the questions match the one in your edition of the textbook, and your problems will be on page 351. Alright, so number 43 asks us to consider the polynomial f of x equals x to the fourth minus 9x squared. Well, in part A, I'm just supposed to figure out the end behavior. So I need to know the degree and the leading coefficient. Well, the degree is 4 and the leading coefficient is 1. Of course, what's important about the leading coefficient is that it's positive. So I know the end behavior will look like this. And if we wanted to state it in words, it rises left and rises right. In part B, I'm asked to find the zeros of the polynomial function. Well, looking at this polynomial, I think factoring out x squared will be a good idea. And then this part that's left over I can factor as the difference of two squares. Giving me 3 zeros. I'm going to go on and write down their multiplicities. Alright, so let's see. Minus 3, 0, and 3 are my zeros. And notice that I only have real zeros. The multiplicities are easy to find here. Multiplicity of that minus 3 is 1. 0 has a multiplicity of 2. And then the last 0 here at positive 3 also has a multiplicity of 1. And we know that as a check, if we found all of the zeros, real and imaginary, we add up the multiplicities, we get back to the degrees. So 1, 2 more is 3, plus 1 is 4. I found all of the zeros, and we've correctly stated their multiplicity. We've also been asked to decide whether the graph touches or crosses at those zeros. Well, we know at the even ones we cross through. At the even ones we just touch and turn around. So at these two odd multiplicities we cross, and at the even one we'll touch. Alright, well I need to find the y-intercept. Plugging in 0 for x here is really easy. I get 0, I get the point 0 comma 0. And if I think about it, right, these real zeros give me x-intercepts. So 0, 0 is also an x-intercept. Well, that's the only point that can be both an x-intercept and a y-intercept. Part D of the question asks me to decide whether the function is even or odd. So I need to substitute I need to substitute minus x in for x and see what happens. Well, what happens is I get exactly the same function I started with, which means this function is an even function. It's going to have that nice symmetry over the y-axis. So anything I graph over here, I'll graph over here. It might even help cut down the number of points I have to plot here in a moment. But I think I'm ready to start graphing this polynomial function. Let's get our zeros on the x-axis. Y-intercept's already graphed by being one of the zeros, and there's not a whole lot of information here, so I do think we need a table of values to help us out. So I'm really thinking about part E now, and I'm just going to pick some x's and find some y's. well, I picked minus 4, 1, 1, and 4 because they're in regions that are between all of my intercepts. So what I need to do now is just evaluate the function. Now, earlier on, I evaluated this particular function using my TI-84 there. And so I know the y values are 112 minus 8. And I know those have to repeat at 1 and 4 because this is an even function. Well, if you wanted to pause the video here and enter those into your TI-84 and make sure I got them right, it'd be a good idea to do that. So go and pause the video and check that out. Alright, well the end behavior says that from this 0 and this 0 I need to rise. These 2 points I would plot at 112, right? Way up there tell me that too. So I know that my function rises pretty steeply. There, so I rise left and I rise right. At minus 1, I come down to the point minus 8, and I can actually plot that one. So 1, 2, 3, 4, 5, 6, 7, 8. Even though I'm kind of going to graph the function through some of my work, that's all right. This point also has to be on the graph by virtue of being there and in my table, and thinking about this as being an even function. All right, well, cross, touch, cross. So I'm going to come through, I'm going to connect the dots, and hopefully have a pretty good graph of this polynomial function. And there's the graph of y equals x to the 4th minus 9x squared. Now if I wanted a better graph, I'd plot more points. I could easily throw in the points at 2 and minus 2 and maybe get this shape a little better. But looking at it, I see that nice, happy, even shape, and we have finished problem number 43. Next up, we're going to go through the same process with just a different function. In number 47, we're asked to consider the polynomial function f of x equals x to the 4th minus 2x cubed plus x squared. So let's go on and get started with that one. Alright, so again we're going to go through that whole process again, finding the degree and the leading coefficients, stating the end behavior, finding all of the intercepts, and plotting more points if we need to. So in part A, again the degree here is 4, the leading coefficient is 1, so we see that same end behavior, where we rise to the left and rise to the right. Part B, we're going to find the zeros of the polynomial. So we set the function equal to 0. And again, I have a function where I have a greatest common factor to factor out front. Factoring out a greatest common factor is the first step to factoring anything. In the parentheses here, I recognize a perfect square trinomial. Cx minus 1 all squared. This will let me write down the zeros, their multiplicity, and decide whether we cross or touch. Alright, x equals 0. Solve x minus 1 for 0, we get 1. Both of those have a multiplicity of 2. So at both of those zeros, we're going to touch and turn around. We're not going to cross through the x-axis. Part C asks me to find a y-intercept, which we already have. 0, 0 is one of my x-intercepts, and again, that's the only point that can be both. So there's a nice, happy y-intercept. Alright, let's find out if the function is even, odd, or neither. Nice little review of a topic from our first unit. We replace x with minus x, and we see what happens. And what I see here is a function that is not exactly the same as the one I started with, nor the exact opposite. Right, only one of the signs changed, 2 of them didn't. This function is neither even nor odd. And with that, we're ready to start graphing our function. don't have very much information to start with, only these two intercepts. Though I could actually get a pretty good graph just knowing that I touch, because my graph's going to have to rise left, rise right, so it's going to kind of just bounce and make a kind of W shape at those two zeros. But we'll plot some more points and get a better graph than just that. Alright, so I elected to plot points at -1, 1/2, and +2. And when I put those in my calculator, I got 4.0625 and 4 again. So I can actually plot all those points, nothing runs too far off the top of my screen, though this point's really, really small, so I'll probably exaggerate the height just a little bit. So -1, 1, 2, 3, 4. +2, 1, 2, 3, 4. And then at 1/2, 0.0625, so not even a tenth. Something that's just barely above the axis. So I think that's, well, I don't think, that's definitely too high, but we'll just let that work for now. I think if we looked at this on our graphing calculator, we probably wouldn't even be able to tell there was a bounce there. So one of the things I always like to point out is by graphing this by hand and understanding the zeros and their multiplicity, I've actually been able to generate a better graph than I get from my TI-84. And that gets us through number 47. So the next up is problem number 54, which again has the same instructions, just asking us to go practice what we know about graphing polynomials. This time with the function f of x equals 1/2 minus 1/2 x to the 4th. So problem number 54. 1/2 minus 1/2 x to the 4th. Now I don't need to, but I'm going to choose to rewrite the original problem before I get started. I always like to look at a polynomial with the part with the highest degree out front. It's supposed to be the leading term after all, and that leading term test is what I'm going to start with. So the degree of this polynomial is 4. And the leading coefficient is -1/2, which gives me an end behavior that falls left and falls right. So, different picture this time. Finally. Part B, I'm asked to find the zeros of the function. Alright, I could factor out a 1/2. What I'm going to choose to do instead is to imagine I actually multiply everything by -2. You could also think about dividing by -1/2. This is going to help me get rid of any fractional expressions. So 0 is equal to, and I carry that -2 through, and I would just get x to the 4th and a -1. And that's going to let me factor that pretty easily. So I see the difference of two squares. And I see the difference of two squares again. Alright, and I can set each piece with a variable equal to 0. And if I only wanted the real zeros, I'd only have to look at the first two factors there. Because I get a 0 at -1, and I get a 0 at +1. Both with multiplicities of 1. But since the instructions just told me to find the zeros, not necessarily just the real zeros, I want to set x squared plus 1 equal to 0. Take 1 away from both sides to get x squared equals -1. And when I take the square root of both sides, I get plus or minus the square root of -1, which is plus or minus I. So this has two imaginary zeros too. And what's nice about that, they only occur once, right? I get plus or minus the square root of -1 each one time. And so I have multiplicities of 1, 1, 1, and 1, which add up to 4. So I needed to find those complex zeros if I was going to use that kind of common sense check. The real zeros give me x-intercepts, so I know I will cross the x-axis at both of those. The imaginary zeros don't, so I don't have anything to say about that. I don't have to answer the question about crossing or touching there because those aren't x-intercepts. All right, in part C, we need to find the y-intercept. Well, f of 0 is 1/2, so the y-intercept is going to be 0, 1/2. And then finally, in part D, we're asked if this is an even or odd function. I'm going to go back to the originally stated one, though it doesn't matter. You could use this one just as well. But if I replace x with minus x, when I raise a minus x to the fourth, I get the same equation I started with. This function is even. It has that nice symmetry over the y-axis. And now we're ready to start graphing our function. I have real zeros at -1 and 1, which become x-intercepts. I have complex zeros, which might affect the shape of the graph, most notably increasing the degree, which changes the end behavior. But they won't appear in my graph as intercepts. I have a y-intercept at 1/2. Well, let's plot some extra values and see what this does, but I think I have a pretty good idea of what the graph is going to do just through those 3 points. So in part E, I can plot a few more points. I elected to plot points at -2 and +2. And earlier I've already evaluated these in my graphing calculator. I got -7.5. And of course this is an even function, so they both have to be -7.5. So why values it look like that? Now, I could also plug in some values at -1/2 and 1/2 and see what it does in here. And I will admit, I looked at my graphing calculator to make sure there weren't any more twists or turns between the x-intercepts and the y-intercept. These complex zeros can do that sometimes. What I saw indicated there wasn't any more kind of turns. That was just kind of this flat diagram that looks like this in between the zeros. And of course, to make my diagram better, I could plot more points. There's a nice happy graph for number 54. Leaving one more graphing problem in 61 and then a application problem in 74 for us to do in this problem set. So let's move on to problem number 61. '61 asks us to think about all the same stuff we've been thinking about in this problem set. But this time with a polynomial function that's in a factored form. So in part A, we're going to have to think a little harder to find the degree and the leading coefficient to state the end behavior. So I just want to imagine I did multiply all of this out. Well, I'd have an x cubed times an x squared times one more x. I'd get a degree of 6. The leading coefficient is sitting right out there, because everywhere else I see an x has a coefficient of 1. So leading coefficient is -2, giving me this end behavior, which falls to the left and falls to the right. Because this polynomial is already in a factored form, finding the zeros is very easy. If it wasn't in a factored form, the first thing I would do would be try to factor it. In fact, this coming week, we spent a lot of time figuring out how to factor things into forms that look like this so that we can find the zeros and interpret their graphs. All right, so let's write down the zeros. Let's see, the smallest zero I'll have is -5. Then I'll have 0 and finally 1. The multiplicity for that -5 is 1. For 0, it's 3, and then finally for 1, it's 2. So I have a little bit of everything here. The odd multiplicities, I know I cross the x-axis. And for that even multiplicity, I know I'll touch and turn around. Now, the multiplicity here of 3, I know that when I go through the graph, I'll have a little bit of a turn in it. So it'll be one of these two diagrams at that multiplicity of +3. Or that's what the graph will look like there. Part C, we're asked to find a y-intercept. Well, f of 0 is 0, so the y-intercept is at the origin. And finally, in part D, I'm asked to determine whether this function is even, odd, or neither. So I replace x with a minus x. Which is a little more interesting here. And what I notice is that when I square this, it has the effect of rendering the minus that's on both terms almost like it wasn't even there, right? It would go away. So this is no different than raising x plus 1 to the second power, so it's definitely a different function. So this is neither even nor odd. Now if you came across a problem like this and you're having a hard time from the algebra test in figuring out whether it was even or odd, remember you're going to graph it in a moment. And at that graph, we'll decide that it doesn't have either kind of symmetry. And we could come back to part D and say, hey, this is neither. It was not even, nor was it odd. All right, so let's plot our intercepts and then see if we can get a picture going. So I have real zeros at minus 5, 0, and 1. All right, and let's see, I'm going to cross through, and then I'm just going to touch and turn around. So I could actually kind of get the shape of this just going from the end behavior. I cross, I touch, and I turn around. So I think the overall shape is going to be something that looks like that. Let's plot a few more points so that we get a more to scale diagram. So in part E, as I like to do, I'm going to pick x values between the intercepts and in the regions to the far left and far right of all the intercepts. All right, and so here I want to show you what happens on this one. So I have minus 2 x to the third times x minus 1 squared times x plus 5. I'm going to go in the table. I'm going to delete out what I have in there, and I want to put in minus 6, minus 3, positive 1/2, and positive 2. And so I get minus 0.3438 at 1/2. I get minus 112. And what I'm going to say is at minus 6, I simply get a really low number. And at minus 3, I get a very high number. And just let that kind of help me graph it. Because what actually happens here at minus 3 at that 1728, right, I have to go off my board by quite a lot to graph it. But I do know what the end behavior does. It falls left, and it falls right. At minus 3, I go so far off the top here that I could just kind of imagine that it goes all the way off and keeps graphing and graphing and graphing and comes back in eventually to come down to this 0 at, well, 0. And I know I'm going to cross through at that intercept with a little bit of a turn. Minus 0.3438. Just there. So something that looks like that, and there at that 0 I see where I'm touching and I'm turning around. And we've gotten a nice picture for number 61, and notice that my polynomial would have to go up quite a ways here, so I'm just going to say that it keeps going and comes back down, let my reader figure that out. And we've got